In this video, we'll present the main concepts from the paper Towards Guaranteed Safe AI, a framework for ensuring robust and reliable AI systems. The framework introduced in the paper consists of three components: a world model, a safety specification, and a verifier. These components fit together into the framework the authors called Guaranteed Safe AI. The goal is to make each component robust enough to provide quantitative guarantees about the safety of the AI system. We can compare this with current practices, in which AI system undergoes some quality assurance, like red teaming and reinforcement learning from human feedback, but provide no guarantees that the system satisfy any safety specification. Let's look at some examples. Suppose we want to translate code from one language to another, for example from C to Rust. The safety specification could require functionally correct code. It could also require that the code be free from specified security vulnerabilities. But how feasible is this? There's been a lot of recent progress in AI applied to mathematics, which is also applicable to proving properties of software. For example, the paper Draft, Sketch, and Prove leverages informal mathematics and autoformalism to formally prove theorems. Alpha Geometry uses a large language model together with a deduction engine to solve Olympiad geometry problems. With additional advances in autoformalism and theorem proving, it may soon be possible to automatically generate code that's both functionally correct and is proven to satisfy a formal specification. For another example, let's consider something far more ambitious: climate stabilization. The goal is to have an AI which can develop geoengineering strategies to verifiably stabilize the climate. The world model would model complex climate dynamics as well as the effects of various geoengineering interventions. The safety specification would encode the desired stabilization properties as well as the health of the planetary ecosystem. Concretely, the AI could propose a sequence of geoengineering interventions, and the world model would predict the resulting climate trajectory. Then, the solution that verifiably stabilized the climate could be executed. Note that this depends on an extremely accurate world model, which can predict all the effects of geoengineering interventions. Why do we need guaranteed safe AI? To answer this, recall that current practices for frontier models like GPT and Claude are evaluation-based. Essentially, this means that the model is tested on various inputs and its responses are observed for dangerous and harmful content. But evaluations only cover a tiny fraction of the input space. By contrast, Guaranteed Safe AI seeks to establish a quantitative bound on the safety of an AI system. To illustrate the importance of this, consider the number of bridge failures per decade. Before the advent of modern engineering, the failure rate was 25% per decade, an astoundingly large number of bridge failures. That number has been driven to 0.4% per decade through the application of better theoretical understanding of bridge engineering. By analogy, we need theoretical and quantitative understanding of AI safety, or we should expect our AI systems to fail, potentially with catastrophic consequences. In addition to proposing the Guaranteed Safe AI framework, the authors also created a safety spectrum for each component and map existing approaches onto each spectrum. The world model spectrum defines the level of safety that can be achieved via various implementations of world models. For example, unsupervised learning may help an LLM develop an internal world model, but this internal, implicit world model cannot be used to directly provide safety guarantees. Here, the approaches colored in green fit into the Guaranteed Safe AI framework, and the ones in yellow do not provide enough details to precisely determine their place on the spectrum. Let's look at the safety specification spectrum. At level 0 is unsupervised learning. And if you ever played with a base model, you know that at times it can feel like you've entered the dark corner of the internet. A step up from that is RLHF and constitutional AI, but these methods ask users or other LLMs to qualitatively judge model outputs and do not provide a quantitative measure of safety. Again, the approaches colored in green fit into the Guaranteed Safe AI framework, since they provide a quantitative safety specification. Finally, we come to the verification spectrum. The verification component ensures that the AI system actually behaves according to the safety specification. For example, Large language models, which have been fine-tuned with RLHF or constitutional AI, may be tested with evals or red teaming to expose harmful content behavior which was not removed during fine-tuning. As previously discussed, this approach can only cover a tiny portion of the input space and does not provide any type of quantitative guarantee that the model behaves according to a specification. The approaches colored in green propose verification methodologies which can provide quantitative verification that a safety specification is met. We've briefly covered the main ideas of the paper Towards Guaranteed Safe AI. We encourage you to read the paper for more details and examples. Thank you for watching this brief paper presentation. To learn more about ae.studio and our approach to AI safety, visit our website at ae.studio or check the links in the description.